Good afternoon, everyone. This is Claudia Shi from Hong Kong Science and Technology Park. Greetings from Science Park, from Tulu Harbor. We are honored to have this opportunity to jointly organize this distinguished speaker series with Hong Kong UST Engineering School. No doubt, this is a very important topic and perhaps it's very difficult, at least for me. But I think we already have reached the attendance, how many? Over 180 now. It's already beyond the screen. I cannot see you, but yeah, welcome all of you. Our belief is innovation is some frontier. Despite the difficulty, the challenges caused by the pandemic, we have been creating all kinds of activities to link Hong Kong with different parts of the world. And this is today's one is a very typical one. We have speakers from ETH Zurich, the Professor Onur Mutlu is a professor of computer science. And we have a moderator who is Professor Tim Chen, Dean of Engineering, Hong Kong UST. And we are all in different places, but we are all connected by this platform, by the desire to share the new knowledge. So I won't take up too much time talking about all these things, but from the bottom of my heart, we are grateful for Professor Onur Mutlu and Professor Tim Chen to give us the talk today. And I wish the talk will be very successful. Just for the audience information, we are going to have more these type of talks. So please keep attention on that. And Science Park hopefully is a place to bring together, it's a convergent point for all of us. Thank you very much. And thank you, Professor Mutlu and Professor Chen. Thank you.
Thank you, Claudia. My name is Tim Chen. I'm today's moderator, and I'm very pleased to introduce my good old friends and Professor Onur Mutlu, who will give a talk in today's HKUST Engineering and Hong Kong Science Technology Park Distinguished Speaker Series webinar. Professor Mutlu is at ETH Zurich as a professor of computer science. He's also a faculty member at Carnegie Mellon University, where he previously held the Strecker Early Career Professorship. Professor Mutlu is also an HKUST senior visiting member of our IAS, Institute for Advanced Study. Onur's current research interests are in computer architecture, systems, hardware security, and bioinformatics. A variety of technologies he, along with his group and collaborators, has invented over the years have influenced the industry and have been employed successfully in commercial microprocessors and in memory and storage systems. Onur obtained his PhD and MS degree in ECE from the University of Texas at Austin, and his BS degree in computer engineering and psychology from the University of Michigan, Ann Arbor. He started his career in the computer architecture group at Microsoft Research and held various product and research positions at Intel, at AMD, VMware, and Google. So today, Onur is going to give a very exciting talk on a timely topic, intelligent architectures for intelligent machines, which I think cannot be more timely because I will mention another co-sponsor of this new talk today, which is the new HK AI Chip Centers for Emerging Smart Systems. So together with the HKUST School of Engineering and the Science Park, this new center address this particular topic. So that's part of the organizer. So the center, I'd like to spend a few minutes to give a brief introduction because I believe many of the attendees today will be of interest to this. The center is named ACCESS, spelling ACCESS. It's a multidisciplinary research center for advancing AI chip design and the design automation technologies to enable novel data-centric computing paradigms, supporting a wide range of AI applications. So ACCESS is also a multi-nation and multi-campus center located in the Hong Kong Science Park, with involvement of more than 25 world-class faculty members from HKUST, from Stanford, from University of Illinois Urbana-Champaign, as well as Chinese U University and Hong Kong University. So the center is now hiring. The center is going to hire a pretty sizable group consisting of principal researchers to senior researchers, engineers, postdocs, and the PhD students. So the detail can be found through the link to this ACCESS job announcement in the flyer of today's talk. If you check the flyer, there's a link. And if you cannot find it, feel free to send email to us. We will share information with you. I spent time to mention this ACCESS is because it's highly relevant to Onur's talk today. And we also look forward to Onur's participation in the new center. Finally, before Onur starts his talk, I'd like to thank again Hong Kong Science and Technology Parks for co-organizing the event. Together with HKUST School of Engineering, I'd like to thank the Science Park colleagues, Claudia, also Billy Lam, Crystal Ho, as well as our HKUST School of Engineering colleague, Diana Liu, along with many other colleagues. So now please join me to welcome Professor Onur Mutlu for his talk on intelligent architectures for intelligent machines. Onur, it's your podium now.
Sure, thank you very much, Tim. I really appreciate the introduction. And I'm going to share my screen right now. Can you hear me well? Okay.
Yes, we can. Maybe you can put the presentation mode.
Okay, sure. Yes, I will do that. Yeah. Yeah, thank you very much. It's a pleasure to be here delivering this talk. And it's thank you very much for inviting me to talk about intelligent architectures and intelligent machines. And I look forward to physically being in Hong Kong at some point. Unfortunately, it was scheduled right before the pandemic and we couldn't make it happen, but hopefully we'll make it happen sometime soon. Okay, so I'm going to talk about intelligent architectures for intelligent machines. And we're going to essentially talk about a lot about data, because today computing is bottlenecked by data, and data is really key for many applications that we are interested in. AI, ML, genomics, anything that you're really interested in, it's usually data intensive. And they require rapid and efficient processing of large amounts of data, and data is increasing on top of this. We can generate much more data than we can process, and you can see this in the top 3 applications that I put up over here, as you can see. And data is really key for future workloads. These are some workloads that we know very well, but they're actually growing. They're being used for very different purposes, also going forward, for example, in genomics. And if you look at that, data becomes a performance and energy bottleneck in all of them. And on the mobile end, which is also a very cutting edge because you're very much limited by energy, the important workloads that we use are also very data intensive. And data becomes a performance and energy bottleneck. And we do a lot of work on genomics and genome analysis. And this is a field that's really important, especially today, for example, with COVID testing and understanding the mutations and different treatment options for different pandemics, for example. Data is growing in genomics at a much faster rate than we can put transistors on a chip today, because the cost of sequencing technologies is reducing significantly. As a result, today we can sequence genomes much faster than we can really analyze them computationally. So this is because, again, data is a performance and energy bottleneck. And this becomes even worse with new sequencing technologies that look like this, that you can fit in your hand and that are really cheap. You can buy this device for $1,000, for example. And you can these devices are actually heavily used in the field today for COVID-19 testing and understanding. So they're actually put to good use today. But basically, in the end, we're very much bottlenecked by the data, how fast we can analyze the data and the performance energy implications of it. So if you're interested, I'm not going to talk a lot about genomics today, but we do a lot of work in this area. And genomics is a very interesting field that combines AI, ML, graph processing, databases, a lot of different things. And accelerating it to enable future applications is a really important area, in my opinion. I'm not going to talk about it, but as I said, we have papers that might initiate you to this topic. This is a survey paper that we wrote very recently, as you can see. And this is a paper that's coming up that accelerates approximate string matching in many different platforms that's coming up in micro. So, okay, my point, I think so far has been clear. Data overwhelms modern machines. It overwhelms the storage and memory capability, communication capability, and as a result, also computation capability that we put into these devices. And in the end, it greatly impacts robustness, energy, performance, and cost. When you look at a computing system, very fundamentally, it has three key components. It has computation, communication, and storage and memory. And so far, over the course of 70, 80 years, what we have done is we have heavily optimized the computing unit. We have many, many mechanisms for it. But I would argue in this talk that we need to optimize the communication and memory and storage units at least as much as we have optimized the computing unit, if not more so. Basically, we have kind of ignored the communication and memory and storage units. As a result, we have a picture that looks like this in many systems that we design. Actually, all systems that we design that I know of. Basically, this is a node. And this is my cartoonish picture of the node. It basically has some processing cores. You can add accelerators to it. It doesn't change the picture significantly. They're connected in some fashion, but most of the system is really dedicated to not doing computation in the cores, but really doing data storage and data movement across these different components. So all the caches, memory controllers, shared memory, interconnects, shared storage, etc., they're all dedicated to storing and moving data. So if you do the calculation, about 5% of a single node today is really the area is dedicated to doing computation, and everything else is there for data movement and storage. And yet we call these devices computing systems, right? Most of the time, most of the area is not dedicated for computation, as you can see. So maybe there's something wrong with this picture, and we'll discuss how we can potentially change it. Okay, so data essentially is a performance energy bottleneck, and this is one result that motivate some of the work that we've been doing. We did this work together with Google and analyzed the workloads that I showed you in this picture over here, and found that more than 60% of the entire system energy is spent on data movement in these workloads in a mobile system, just moving data across the hierarchy. And this is because we have of the way we design the architectures today. So I will start with this axiom. I will basically say an intelligent architecture has to be designed to handle data well. But of course, the question is, how do we do that? How do we handle data well? I will say there are at least three ways of doing this. We need to ensure data does not overwhelm the components we design via intelligent algorithms, via intelligent architectures, and even more importantly today, I believe via whole system designs, all the way from algorithms, architectures into the devices. If we can optimize across the stack, we can come up with a much better place, and we can actually have a much better solution to the data problems. Okay. On top of this, I believe you need to design the system such that we can take advantage of vast amounts of data and metadata, such that we can improve architectural and system level decisions. I will talk about this a little bit more, and I will spend a little bit less time on this, but this is also very important. Can we actually design an intelligent system that can understand what's happening to the data and that can adapt its design decisions and to such that it can do better decisions going into the future? As humans, we do this a lot, right? For example, when I touch my hand on a stove that's hot, I quickly figure out that I don't do that again, right? I should not do that again. Machines we design are not like that, unfortunately, today. They make wrong decisions, but they keep doing the wrong decisions over and over and over and over because they cannot adapt their policies in a learning-based fashion. And I think using machine learning and artificial intelligence to actually both design the machines and change the policies dynamically is a very good directions that we need to explore going into the future. I think third thing we can do to handle data well is to understand and exploit properties of different data. If you look at systems we design today, especially the general purpose systems, we don't know much about the properties of data. We don't know about the security properties, compressibility properties, approximability properties, and various different properties. But if we knew that information, if we gave that to the system from the higher level, semantic information, we could improve both the algorithms and architectures and various metrics. So I'm going to talk about these three things in this talk, especially focusing on the first part. If time permits, we will spend time on the second and third parts also. This doesn't mean that the second and third parts are not important. It just we just don't have enough time to talk about all of them. Okay, the corollaries. How do we actually stand based on how we should handle data today? If you look at how architectures are designed today, I will posit that architectures are not good at dealing with data. They're designed to mainly store and move data versus to compute, as I showed you earlier. This is because they're processor-centric as opposed to data-centric. And we're going to tackle the question of how do we make architectures much more data-centric. The second is architectures are not good at taking advantage of vast amounts of data and metadata available to them. As I mentioned, they are designed to make simple decisions, ignoring lots of data, and they cannot correct their mistakes. They keep making the same simple decision that ignores the data, and that decision may not be correct. For example, the memory controller that I have on my cell phone or on my computer right now is executing the exact same algorithm that it was designed to execute 5 or 6 years ago. Yes, it's that old. But it has not learned anything, even though it's executed lots and lots of programs. It has not learned anything. It has not adapted its algorithm or policy at all. So this is because it's designed in a human-driven manner as opposed to data-driven manner. If it were designed in a more data-driven manner, it would learn from its past actions and change its policies. And I think this is a very good direction to explore. And the third one is architectures today are not good at knowing and exploiting different properties of application data. They're designed to treat all data as the same, regardless of its security properties, privacy properties, compressibility, approximability, whatever you can think of, or locality even. This is because they make component-aware decisions as opposed to data-aware decisions. And this is mainly because the communication across the different parts of the stack is lacking. We cannot communicate semantic information from the algorithms and programs into the architectures, hardware, and devices. So if we could actually do that, we could actually have a much better system, in my opinion. So as I mentioned, we will tackle all of these, but we will start with the first one over here. So I call this data-centric or memory-centric architectures. How do we design systems to be, let's say, respecting data much better? And these are 4 different properties that I list over here that I believe are important for designing such systems. I believe we're going to talk especially on the first one. We need to process data where it resides, where it makes sense. This brings us to processing in or near memory structures. But I believe we also need to enable low latency and low energy access to vast amounts of data. This brings us to low latency and low energy memory, which is really important to investigate, especially when we process data where it resides. I will not talk about this, but there's a lot of work that we are doing and others are doing in this area that I would recommend. We need to store data at low cost and process it at low cost. We get high capacity memory at low cost. This brings us to emerging technologies, hybrid memory, interesting compression algorithms. I will again not talk about this, but this is a part of data-centric architecture. And finally, intelligently managing data is important. Having intelligent controllers handling robustness, security, and cost is important. And I will briefly mention this to motivate processing data where it resides, but this is actually a component by itself. So these are 4 properties that we want from a data-centric architecture. And I believe these are related to each other. It's not like they exist independently of each other. If you actually enable all of these properties at the same time, you get amplification beyond what each of them can provide alone. Okay, so let's start with the first one, processing data where it resides. I call this processing data where it makes sense. Today, we're processing data only where the computation units are, and computation units are actually only in the processor or the accelerator, as far away from the data. Everything else that's close to the data is not able to do computation. They're just moving data or storing data or keeping data intact. So why don't we actually enable computation everywhere else as well, have a distributed system that can have distributed intelligence across the entire system? So this is what this topic is about. And this is not a new idea. This is one of the oldest papers that I found on the topic. It's in the general purpose domain, of course. It was written by Harold Stone. It's called A Logic and Memory Computer. It's, as you can see, the reference is from 1970. He did this work while he was at the Stanford Research Institute. But basically, people wanted to actually put computation near memory or inside memory for decades and decades and decades. And unfortunately, it has not been very successful. But I will argue that today we're in a very different situation. And hopefully, let me give you why I think that way. Basically, there are 2 reasons why we're kind of constrained in the middle, and we really need to look at a paradigm change to enable in-memory computation and more generally computation near data, wherever data resides. It could be in storage, it could be in cache, It could be while the data is traveling through the network, interconnect, etc. And the first reason is we have a huge push from technology. And the second reason will be we have a huge pull from systems and applications. So let's look at the first reason over here. Today, memory is not scaling very well. We are having a lot of difficulties in terms of technology scaling of memory. As a result, performance improvements, energy improvements, and even capacity improvements, which main memory is really designed for, is coming at a big cost. And as a result, industry is investigating controllers close to DRAM, and for maybe after a really long time, industry is actually open to new memory architectures, which was not the case for decades and decades and decades. So you can see architectures that look like this, where you have a logic processing layer underneath memory layers, and you can see similar architectures like this, and some other architectures actually do some processing inside the chip. And actually, there are some newer technologies that are under development that are more monolithic 3D. Okay, these are driven by memory scaling issues. This is actually a paper that I had presented in the International Memory Workshop in 2013, where we argued that memory scaling is going to be a huge problem. At that time, we didn't have evidence, but later we actually went out and collected evidence. And I'm going to talk to you about some of that evidence to motivate this technology problems that lead to doing something different with processing data near memory. Okay, so this is one study that we did with Facebook. Basically, we analyzed all of the memory that they have in the system and looked at all of the memory errors. We categorized them. And basically, this is one conclusion from the study. Essentially, if you're employing a higher density chip in the server, and they have many, many servers, so this is data aggregated across many, many servers, millions. And you can see that the server failure rate is directly correlated with the density of the chip that's employed, meaning that higher density chips imply a higher error rate. And this is because DRAM cells are closer to each other, and you get vulnerable to a lot more noise in the memory chips. So as memory scales, it becomes much less reliable. So if you're interested, you can take a look at this paper. And this is one of the evidences showing that memory is becoming less reliable, and we need to do something about it. And then we went on and we looked at infrastructures. We developed some infrastructures. These are FPGA-based infrastructures to actually test memory chips and to understand what's going on in the scaling issues in memory. What kind of problems are we having with reliability, retention times, latency, and many different issues. And we did analyze many different issues. This is one of the infrastructures where we discovered the rowhammer problem, which I'm going to talk about. And we actually open source this infrastructure. Many people can use it. It's C++ programmable, as you can see. And we'd be happy to support it. Other people have been using it in academia as well as in industry. So while we were doing a lot of the studies that we were doing, we found out that existing DRAM chips are actually vulnerable to a bad type of error, which is one can predictably induce errors in most DRAM memory chips that you can buy in the field. And this is called rowhammer today. Essentially, more than 80% of the tested DRAM chips at the time were vulnerable. This was 2012, 2014 timeframe. And this is really the first example of how a simple hardware failure mechanism can create a widespread system security vulnerability. And you can see that people are writing, I don't want to call pop articles, but technical articles that are relatively lightweight that say, forget software, now hackers are exploiting physics. This is about rowhammer, essentially. So let me give you the problem very, very quickly. It's a disturbance error. It exists in many types of memories. Now, basically, whenever you activate or read or open a row in DRAM, you apply high voltage to it. And if you want to read another row or activate, you need to activate another row, you need to apply low voltage to that row. So this is called an activate and precharge pair in DRAM. So if you keep doing this, activate, precharge, high voltage, low voltage, high voltage, low voltage, high voltage, low voltage, high voltage, low voltage, enough times before the cells get refreshed, it turns out in rows that are physically adjacent to this row that you're hammering, you get bit flips. Clearly, this is not supposed to happen, right? Because you're not even touching, you're not even writing to memory. You're not even writing to the row that you're accessing, but you're really flipping bits that are just adjacent. This should not happen. We call this the hammered row. We call this the victim row. And we basically showed that more than 80% of the chips that we've tested from all three major manufacturers, and there are three major manufacturers in DRAM today, are vulnerable. And this is a scaling problem because this problem was not exposed to real DRAM chips before chips that were manufactured before 2010. And all of the chips that we tested that were manufactured between 2012 and 2013 were vulnerable to this problem. So at some point, the cells became too close to each other. As a result, the noise that you induce because of these activations and precharges started affecting cells that are nearby. And you were able to actually induce enough disturbance by doing some number of activates that you could actually fit into a refresh interval. And if you're interested, I'd be happy to talk about this more, but you can also look at some of the works that we've done in Rowhammer. And we said that this is actually a security problem in addition to a reliability problem. One could take over an otherwise secure system if you don't provide memory isolation. And memory isolation is a key property of a reliable and secure computing system, and access to one memory address should not have unintended side effects on data stored in other addresses. I still believe this very strongly. And we said that someone can actually hijack your system by inducing these bit flips intelligently and taking over your system. And good folks at Google Project Zero did exactly that. They showed that they could actually take over an x86-64 Linux system by actually inducing these bit flips in vulnerable laptops by replicating our results. So you can see that because of these scaling issues in memory, because cells are getting too close to each other, we're having reliability problems that are now affecting our security. And this is a serious security problem today that is currently unsolved. I'm going to give you the later story also in a little bit. But to solve this problem, I believe we need intelligent controllers. If you actually have a patchable memory controller in the system, once you identify a problem like this, you can actually patch your memory controller to find some solution. I'm not going to talk about solutions in this talk, but one solution could be actually have a controller that intelligently and selectively refreshes adjacent rows such that they don't get these bit flips. And we have proposed that solution. Some of it is actually being employed in the field, but more needs to be done. So clearly memory scaling issues are real, and this is our paper from 2014. And we recently wrote a retrospective in Rowhammer. If you're really interested in this problem, this retrospective covers all the way from devices to security attacks and different kinds of solutions to the problem. But this paper is not the state of the art at this point, unfortunately, because there's some work that has happened in 2020 that show that Rowhammer is becoming much worse. This is our experimental analysis in 2020 in ISCA. And I'll give you very quickly the key takeaways showing that scaling problems are actually going to get much worse. Basically, we examined more than 1,500 DRAM chips, and we found out that chips are becoming much more vulnerable to Rowhammer as technology scales to smaller node sizes. And there are some chips today where weakest cells fail after only 4,800 hammers. Basically, this is 4,800 activations, which is not good because as you reduce this number, it's easier to do the Rowhammer vulnerability. And chips of newer DRAM technology actually exhibit Rowhammer bit flips in more rows and farther away from the victim row. So the problem is becoming much worse, basically. And on top of this, existing mitigation mechanisms are not effective. So we really need better mitigation mechanisms. And I believe having intelligent controllers is part of that mitigation mechanism or solution mechanism. And on top of this, we actually did some work that showed that existing solutions that are out in the field that are provided by DRAM manufacturers are unfortunately not working. We showed that you could actually bypass these solutions that are called target row refresh. We call this work trespass. You could automatically bypass these solutions, and essentially you're back to square one because the solution is not secure enough. So we really need secure solutions to the problem, and I believe that comes with intelligent controllers. And if you're interested, there's some other work that we have done in on this topic in 2020. And I don't have enough time to talk about Rowhammer, but hopefully it's clear that because of the push from circuits and devices, we really need intelligent controllers to solve the scaling problems that we have. And I'm not really advocating anything new in a sense, except things are new in DRAM. Because if you look at flash memory, for example, an SSD has a very intelligent controller that understands all of these scaling problems and reliability problems and corrects the errors in many, many different ways. So we already have an example of an intelligent controller in an SSD, solid state drive, which is in all of our devices, as you probably know. We just need to do it in DRAM. Of course, DRAM has its own challenges because you're at main memory and the latencies are very low. So you need to be very careful when you actually put intelligence over there, as we will discuss later on also. Okay, so very quickly, there are other reasons. Rowhammer is not the only reason. There are many other reasons why we want intelligence in the memory controller. And one of the reasons is another scaling problem with DRAM, which is retention times. Essentially, DRAM requires refresh, and you need to know the retention time of DRAM. And it needs to be refreshed every 64 milliseconds. Actually, today it's every 32 milliseconds or so. But this is not good because you're refreshing everything every 64 milliseconds, and this is causing energy and performance problems. So one of the ways of solving the problem is actually understanding the retention times of different cells and adapting the refresh rate to the retention times of different cells. And I'm not going to go through the detail, but if you have an intelligent controller, it can understand these retention times. But it requires more intelligence than what I just suggest over here, because it's not an easy problem. The problem is location dependent. The retention time is location dependent. It's dependent on the stored values. It's dependent on time as well. So you really need to design an intelligent controller to be able to do this. And if you do that, you can actually save a lot of the refreshes. And I'm going to flash some of the papers that we have written on this topic. And I'd be happy to talk about this going forward as well. But okay, if you want to solve the refresh problem, I believe that you need an intelligent controller as well. So it's not just us academics talking about the problem. Industry is actually writing papers about this too. So you can see that this is a paper that's written by two companies that don't normally talk to each other, Samsung and Intel. And they've written this paper. Sorry, I'm hearing some noise. Hello? Is there a question or? Okay. Okay, I'll continue. Basically, you can see that Samsung and Intel, this DRAM design team, circuit design team, and Intel memory controller teams got together and basically said, there are difficult challenges that we have in DRAM. So we actually want to architect controllers and DRAM together to enhance the process scaling. So this is the push from technology that I showed you earlier, in a sense, validated by two major companies. Okay, so we're at a point today, we want controllers close to DRAM and intelligence close to DRAM. Let's take a look at the systems and application side. I'm going to repeat this in this slide over here. Basically, we have three key systems and application trends that are pushing us towards intelligence and computation near and inside memory. First of all, data access is a major bottleneck, as I mentioned earlier. Energy consumption is a huge limiter today, which was not the case for decades and decades. And data movement energy dominates compute today. I'm going to handle all of this in a little bit, but this is true especially for off-chip to on-chip movement. In my opinion, there's an even bigger issue, which is, do we want a world that looks like this, beautiful, sustainable, where we can breathe? Or do we want a world that looks like this, very productive, but maybe not sustainable? I would argue that we want, in a sense, both. We want sustainability, absolutely, but we also want high performance and productivity. And on top of that, we want energy efficiency. So the question is, how do we get all of them? I will argue that the problem occurs because we're not handling data well. So data access today is the major performance and energy bottleneck. It's leading to energy inefficiency and as a result, non-sustainability. And our current design principles are causing great energy waste because we're actually processing data far away from the data. And these actually cause great performance loss as well, but we try to mitigate this performance loss a lot by designing our systems, maybe over-designing our systems. Because data is far away from the processor, we actually put a lot of mechanisms into our systems to tolerate the memory latency and memory bandwidth issues by adding prefetching, by designing very sophisticated processors, by adding multi-threading, by adding many levels of hierarchies. And all of these are there because data is being processed far away from where data is. And this may be mitigating our performance loss, even though, although that's not exactly true, as I will show you in a little bit. Maybe some of it is being mitigated, but it's causing more energy waste. So we're in a vicious cycle today because we're not doing the right thing. Let's say we're not processing data close to the data. We're moving data a lot. As a result, we're wasting a lot of energy to begin with. And on top of that, we're adding a lot of complexity to our systems to mitigate the performance loss. And that's wasting a lot of energy on top of that as well. So we're in this vicious cycle where we keep wasting energy to get performance because fundamentally processing of data is performed far away from the data. And if you look back at this computing system that I mentioned over here, it has computation, communication, and storage memory as components. This is because we're very processor-centric today. And as a result, processor is considered the master and everything else is dumb and largely unoptimized. And as a result, we have this huge problem with data. Yet we know that this is a big performance problem. I will give you a little bit of history over here. This is an article written by Dick Seitz, who was the chief architect of alpha processors in 1990s. And his team designed this beautiful alpha processor in 1990s. And after that, he wrote this one-pager article in Microprocessor Report that you can read, you can find online. He basically analyzed the processor together with his team and found out that, says in this article that we designed this processor that's capable of finishing 4 instructions per cycle, but this processor is finishing 1 instructions every 4.7 cycles, meaning that it's operating worse than 1/18 of its peak bandwidth. And he says that this is happening because it's waiting for memory most of the time. So memory system is really the bottleneck. And as a result, he finishes the article saying that I expect that over the coming decade, memory subsystem design will be the only important design issue for microprocessors. And I believe he's right, because if you look at all of the AI chips that are being designed today, they're actually adding a lot of memory into the system. and they're trying to do processing close to the memory. And the title of the article is "The Memory Stupid." It's really a play with the elections that were coming at that time in the U.S. One candidate was running, Clinton was running with "It's the economy stupid" at that time. Okay, so to fast forward 10 years later, this is data from my own PhD thesis. If you look, we actually analyzed Intel's workloads at the time that Intel used to design all of their general purpose processors with, and we found essentially the same thing. Most of the time, the processor is waiting for data. And if you're interested, we have a lot more results in the first paper that I've written academically. And if you don't believe me, if you don't believe Dick Seitz, since everybody believes Google today, this is data from Google in their beautiful 2015 paper that was published at ISCA. They basically analyze all of their data center workloads. You can see that a lot of them are video, search, indexing, AI related, in addition to other stuff, as you can see. And they basically say most of the time the processor is waiting for data, this red part essentially, and the processor is finishing instructions only 10 to 20% of its execution time. And you can see more analysis in this paper. I would recommend it if you're interested in this topic. Essentially, the processors we designed have improved clearly over the last 3 decades, but they're still waiting for data. Okay, so essentially we have a processor-centric design. This leads to grossly imbalanced system. As a result, we are energy inefficient, low performance, and complex. And to tolerate this, we have overly complex and bloated processors and accelerators, but this leads to even more energy inefficiency, performance issues, and complexity, because we could use those resources for improving performance in much better ways, potentially, right? If we didn't have a processor-centric design. As a result, we're back to the picture that I showed you earlier. Most of the system is dedicated to storing and moving data. Okay, let me give you the energy perspective quickly. These are slides that I borrowed from Bill Daly from his high-peak keynote. It's about 5 years ago, so the numbers are a little bit off, but still the picture is similar. Essentially here, he compares different operations in a system and basically says a 64-bit double precision floating point operation costs 20 picojoules of energy. This is a very complex operation. And a DRAM read or write by itself, 8 bits, 64 bits, let's say, it costs 16 nanojoules. So this is about 800x difference. So a single memory access is, let's say, between 2 to 3 orders of magnitude more costly in terms of energy compared to a complex addition. And this is not very good, clearly. For example, if you have a workload that doesn't have a lot of locality, like in graph processing, for example, you're doing a lot of random accesses through a graph. And if you want to add 2 floating point numbers, does it really make sense to bring those 2 floating point numbers by doing 2 memory accesses and then write back the result by doing 1 more memory access? You're consuming 3 times 2 to 3 orders of magnitude energy to do a very not so sophisticated anymore double precision floating point operation. So if you go back, let's talk about history a little bit. If you go back 70 to 80 years ago, when computers were first being designed, general purpose, this picture was not like this. The picture was actually the opposite. In a sense, a complex operation was about 2 orders of magnitude or so more energy hungry and performance hungry than a memory access. So what happened over the course of 80 years? I will say basically technology scaling. We were very good at scaling technology node to smaller nanometers, and that helped logic gates very well, but that didn't help the interconnects and the capacitors. As a result, what happened was interconnect did not scale. So all of the latencies and energies were more or less constant, let's say, not exactly, but more or less constant compared to logic. And as a result, we're 5 orders of magnitude on the other side, and memory access is much more costly today. So, but we're still designing processors in a processor-centric manner. Okay, so if you're interested, you can read more papers that essentially show the same thing. Depending on how we optimize the memory system and the add operation, the number is about 2 to 3 orders of magnitude. And as a result, we have this picture that I showed you earlier. More than 60% of the entire system energy spent on data movement on important workloads that we really care about. So basically, I will argue that we do not want to move data at all. Essentially, we need a paradigm shift to enable computation with minimal data movement. Compute where it makes sense, where data resides, as opposed to where the processor is or the accelerator is. Basically, we want to make computing architectures more data-centric. I will focus more on processing inside memory today, but as I mentioned, this is a more general paradigm. Processing in the interconnect, in the caches, processing in the storage while the data is moving. So we really need to enable that everywhere, in my opinion, to be able to enable really intelligent systems. But let's talk about memory, because memory is really interesting, especially main memory is really interesting because it's really close to the processor. and it's big, and it can store a lot of things in memory today. We have a lot of in-memory databases today, for example. But let's assume that we store the data that we're really interested in memory. Then we would like to be able to ask questions to memory. Memory, can you do this for me on the data? And the memory says yes or no, and the memory responds with the results it can do. And then you can actually talk to memory as an intelligent agent so that you can actually achieve what you're doing in a very intelligent way. So clearly there are many questions over here. How do we design the compute capable memory and the controllers? How do we design the processor chip and the in-memory units? How do we design the software and hardware interface to enable this? We do not have these, but there are potential movements toward that area. How do we design the system software compilers and languages to enable this? And on top of that, how do we design the algorithms and theoretical foundations? Basically, this is really across the stack problem, going from all the way from algorithms to devices, because devices can also be designed to actually do computation, not just storage and memory. And I said theoretical foundations over here because those of you who may have taken computer science, computer theory courses may know that whenever you're actually looking at the complexity of an algorithm, today we're counting operations. But if memory is the bottleneck, maybe we really need to rethink how we actually theorize about the computational complexity of our algorithms. It's not just counting operations, because counting operations may not be that important if you're spending most of your time and energy in memory. Okay, so I'm going to talk about processing in memory. Clearly, this is an area that has been investigated before, but I'm going to talk about two approaches that are relatively new to the area. In the past, people have investigated putting large chips, large processors inside DRAM or some main memory. I think this is also good to investigate today. Maybe you don't want as large chips because of thermal issues and cost issues. DRAM and logic processes are not very compatible with each other. But if you're frugal about it, maybe there's a space to investigate that also. But I'm not going to talk about that direction. I'm going to talk about two different directions that I believe are really interesting. And the first direction is really, how do we minimally change memory to do computation in addition to memory and storage capabilities? And it turns out, I'm going to talk about DRAM specifically, but well, clearly DRAM is almost all the main memory market today. It's a huge market, $45 billion and growing. But there are other technologies that are also interesting. And I believe whatever I describe over here is actually applicable to any memory, not just DRAM, although I'm going to give you specific examples from DRAM. And if you look at memory, memory chips have great capability to perform bulk data movement and computation internally with small changes. You can exploit internal connectivity to move data. You can add internal connectivity to do even better. And you can exploit analog computation capability. And you can actually add slightly more analog computation capability as well. So I'm going to talk about some examples of this. And I'm going to start simple. I'm not even going to talk about computation to begin with. I'm going to talk about data copy and initialization, which is really important because whenever you're doing many different operations that look like this, you need to copy data or you need to initialize data. My favorite example for this is you have a huge 1 terabyte database. Initially, you need to initialize some tables for it. And initializing a 1 terabyte database to zeros or whatever value you want to initialize it with takes a long time. So startup cost of systems actually is dominated sometimes by initialization. And Google in the paper that I mentioned earlier actually analyzed the cost of just two system calls, memo and memcopy. This is not all of the data copy initialization. This is the data copy initialization initiated by these two function calls. And they basically said just these two function calls account for about 5% of the cycles in their data center workloads. This is a lot actually. And in the paper, they say a lot also. And they say basically approaches that are similar to what I'm going to describe next are actually very interesting to investigate. So let me describe that approach in a little bit. But before we describe that approach, let's take a look at how we do bulk data copy today in our systems. Let's assume that we have a 4 kilobyte page. We want to copy it to another 4 kilobyte page over here. Today, we have to go through the processor, basically bring the source page byte by byte into the L1 cache, bring the destination page byte by byte into the L1 cache, do the write, and write back the destination page. I'm not showing that over here. So clearly, this is high latency because you're going through the memory bus, and it's 4 kilobytes. Imagine doing this for 1 megabyte and then 1 gigabytes. So latency increases clearly. This caused a lot of bandwidth utilization on this memory bus that could have been used for something else while you're moving this data. This causes cache pollution, but you could eliminate that by doing this through the direct memory access and the memory controller. I'm not going to talk about that, but it's doable. And this causes unwanted data movement. Imagine that you're just initializing rows or copying data, but you're not going to use the destination for a long time. You're bringing data for no reason into the caches. So today, for a 4 kilobyte page copy via the direct memory access engine, not even going through the caches, it takes about 1,000 nanoseconds and 3.6 microjoules, which is a lot for 4 kilobytes. Now, if you show this picture to a, let's say, 10-year-old child and ask the question, am I doing this right, given all of this I described, maybe they will tell you, well, why don't you just do this in memory? And that's basically what we're going to show. And this is not clearly, not in a sense, let's say rocket science, but this is an option that we would like to enable in systems that are not there today. So what would this do? Basically, if we could exploit the internal connectivity in memory to be able to do this, we could do this at low latency. We could do this at low bandwidth utilization. We wouldn't use the bus over here, no cache pollution, and no unwanted data movement. So I'm going to show you a mechanism that takes us 1,000 nanoseconds to 90 nanoseconds. You could optimize this even more, and 3.6 microjoules to 0.04 microjoules. So almost 2 orders of magnitude improvement. Okay, so the idea is very simple. We call it row clone. It's the in-DRAM row copy. You can almost do it in existing chips. In fact, I'm going to tell you a story about that later on. Basically, what we would like to do is, this is a DRAM subarray. The source row and the destination row are in the same subarrays. You first activate the source row, which brings the data into the row buffer. And now the cells that you've activated are strongly amplified in the row buffer, because this is an SRAM structure, if you know how DRAM operates. Now you basically copied the data into something really, really strong. Now the next step is basically just sending another activate to the destination row. Now, if you do this, you disconnect the source row, of course. The data that you've amplified strongly from the source row gets written into the destination row, because the sense amplifiers are much stronger than the destination cells over here. Basically, by doing 2 consecutive activates, we're able to copy data from row A to row B by using the row buffer in the subarray as an intermediate storage structure. And I believe this is the best you could do with DRAM technology without adding anything into the system, and it's negligible hardware cost. And you can read our paper for more detail in terms of how do you do it between banks, how do you do it between subarrays. We have new mechanisms actually to do this after this paper. So I'd be happy to point you to those new mechanisms. So ignore these numbers for now over here. But if you're doing the best case, which is intra-subarray data movements, your latency reduces by more than an order of magnitude, and your memory energy to actually do this data movement reduces by 74x in this case. And we actually have mechanisms that reduce the interbank and intra-subarray movements closer to over here. So these numbers are actually from 2013, as you can see. Okay, so this is the paper that introduces the idea. Essentially, what we're thinking of DRAM with this mechanism is memory now has some specialized computation capability. Well, in this case, data movement and initialization capability. And I didn't talk about initialization, but initialization is just a special case of copy, right? You initialize one row to all zeros, and then you copy that row to all of the other rows in the system, such that you can initialize things much faster. Essentially, we're adding specialized capability to memory in terms of what is really good at. Essentially, we're treating memory as an accelerator. We know how to design the accelerators over here, and we invest a lot into these accelerators. So why don't we invest a little bit into the accelerators that are close to memory, which are very unique because they're sitting on the right side of the memory bus as opposed to the left side of the memory bus. As a result, they're not bottlenecked by the memory bus. And they have low latency, high bandwidth, low energy access to a huge amount of memory over here. But programming may be similar to other accelerators. Okay, let me give you a little bit more. Basically, we can do more than copying and zeroing. We can do and, or, not, and majority. We call these in-memory bulk bitwise operations. You can do this at low cost and by using analog computation capability of DRAM. The idea, as I will show you in a little bit, activating multiple rows performs computation. And as a result, you get significant performance energy improvements, and you can read the paper in detail. At this point, I think it's important to say that new memory technologies enable even more opportunities. So these are analog operations, but new memory technologies like memristors, RAM, phase change memory, STT-MRAM, actually can operate data on minimal data movement because they're non-volatile. In DRAM, fundamentally, you're destructive. Whenever you need to operate on data, you destroy the data first, so you need to move it somewhere else a little bit. But these new memory technologies, you can actually do matrix multiplication with minimal data movement, for example. And I believe they're actually a very good fit for doing machine learning and AI acceleration. I believe DRAM is also a very good fit, but maybe you can get even better efficiency with new memory technologies. Okay, I'd be happy to talk about that further. We have work going on in this area, and there's a lot of work that I will briefly mention one of them later on. So let's talk about DRAM. How do you actually get very simple and or operation in DRAM? So these are 3 rows, A, B, C. I'm showing only one cell, but imagine that there's 8 kilobytes of cells, and imagine that we have this is within a subarray. You could do this in thousands of subarrays. So you could do what I'm going to show in 8 million bits in a single DRAM chip, in a single DRAM cycle, let's say. So what are we going to do? We're going to actually activate all of these rows at once. And if you do that, based on the fundamental charge sharing characteristics of the circuit, if at least 2 of these cells are charged, you get the charge state at the end in the sense amplifier. If at least 2 of these cells are discharged, you get the discharge state. So what does that say? Basically, logically, this operation is really a bitwise majority function. Now, bitwise majority is a great function. You could actually do a lot with it, but you could actually rewrite it this way also by taking C out. You get the, if you set C to 1, you get the OR of A and B. If you set C to 0, you get the AND of A and B. So now you have bitwise AND or OR. And you can expose this to the instruction set architecture. And then I'm not going to go through this in detail, but you could actually have an instruction like this. And you could internally, that instruction can be translated into row clone operations and activate operations to keep the costs very low in the DRAM chip. And the cost is relatively low. So you can do bitwise AND and OR. But we also have bitwise NOT, because that enables functional completeness. If you have bitwise AND and NOT, or OR and NOT, now you can actually have a functionally complete system, and you can implement any algorithm as long as you can efficiently translate the algorithm into bitwise, block bitwise operations. I'm not going to talk about the details of the NOT, but actually the complement of a cell already exists in the sense amplifier. We just connect it back into the array. And that's the idea. If you're interested, you can read the paper for more detail. But what this really buys you is a very high performance NOT in DRAM, as you can see, and OR are actually very high performance also. And then on top of this, you can add other primitives, NAND, NOR, XOR, XNOR. And you get basically significant performance improvement and energy reduction. Now, let's talk about workloads. Of course, it's good to do this at the bottom layer. Now, how do we actually take advantage of at the algorithmic layer? So we actually looked at many workloads that can do block bitwise operations. I believe any workload that can be translated into these block bitwise operations can work, but some workloads are actually much better fit because they're already operating on block bitwise operations, like bitmap indices in databases. Some databases are actually designed for this purpose. Some web search engines, like the Bitfall engine from Microsoft, are actually designed to maximize block bitwise operations. And there are other stuff, as you can see, DNA sequence mapping, encryption, etc. And let me give you very quickly some performance results. These are end-to-end performance results on the execution time of a query on a database that uses bitmap indices. And you can see that end-to-end execution times can reduce by 5 to, let's say, 6.6x, which is significant. And this is a database that's specifically designed for maximizing block bitwise operations. And you can see that the performance improvements are even higher on the queries that we see. And one of the other benefits is, as the data size increases, performance improvements also increases. Clearly, it saturates at some point because you cannot fit all of your data into a single DRAM chip and you need to scale. But 12x is significantly higher. It's more than an order of magnitude end-to-end. Okay, so if you're interested, I'd recommend taking a look at these papers. And we have recently written this book chapter that talks about block bitwise execution in DRAM. And there are some research directions that we identify over here. Now, the interesting thing is some of this is already possible in existing DRAM chips. So when we wrote the paper, we got some pushback saying that, oh, you have to change the DRAM chips to be able to do that. No one's going to do that. Later in Micro 2019, this paper was published. Basically, these folks using our soft MC infrastructure that I mentioned earlier, they basically showed that they could do row clone cleverly by actually reducing the timing parameters between two activates in off-the-shelf DRAM chips without modifying DRAM at all. They basically modify just the memory controller. They also show that you could do operations like what we've described, block bitwise operations, in some memory chips with some sort of reliability. So basically, this shows a proof of concept that these operations are not really that far as some people may think of. We could actually slightly change the DRAM chips to actually enable these operations in a very reliable manner. And actually, some DRAM chips are already able to do it, except we don't have, of course, reliability guarantees because the chips are not designed for that purpose. So as you can see, these operations are relatively simple, and there's a proof of concept that's out in the field. And we're not restricted to DRAM again. As I mentioned, these folks showed that you could do similar operations, block bitwise operations, in phase change memory, for example, and other resistive memories. So the ideas are general, as you can see. Okay, let me talk about the second approach relatively quickly, and then we'll switch gears a little bit. So the second approach is exploiting 3D stack logic and memory. And this is very opportunistic because these things already exist today. We have high bandwidth memory, hybrid memory cube, and we have other true three-dimensional monolithic 3D technologies that are under development that I believe are also very, very interesting, especially processing from a near data processing perspective. And clearly we have these existent, and you can take a look at some of the papers that we have written and others have written. So while we were looking at this, we had two key questions in 3D stack memory. How can we actually accelerate in a specialized manner some applications such that we can get a lot of benefit? What is the maximal performance benefit that we can get by having the freedom to change the entire system? It's always good to look at this. And then we actually stepped back and said, okay, we don't want to change the entire system by if we simply offload functions to the logic layer of 3D stacked memory, what benefit can we get? And then there's a minimal approach we also wanted to investigate, saying what are the minimal changes to system and programming that we can do without disturbing the system a lot by getting some benefit out of 3D stacked memory, where there's a logic layer where you can do computation near memory. So let me talk about the first one, because first one is actually very interesting. It's kind of, you had the freedom to change the entire system. What would you do? And we focused on graph processing at the time, and graph processing is really important. There's a lot of applications that use graph analytics. In fact, in genomics today, we're using a lot of graph processing. And scalable large-scale graph processing is challenging. If you throw cores at the problem, you don't get performance, because fundamentally it's memory bandwidth bottleneck, because you have a lot of frequent random memory accesses and you have little amount of computation to cover for it. So this is the system we designed. I'm not going to go into the detail, but I'm going to describe a high-level picture. The paper that I mentioned over here has a lot of detail on the entire system. Again, it's designed from algorithms to logic all the way. We don't change the devices significantly, but you could imagine changing the devices, meaning the logic layer, how the logic layer is composed of. So we take advantage of the logic layer. In the logic layer, normally you have what's called vaults. It's divided into vaults that are interconnected with some network. In the vaults, you normally have a DRAM controller. The DRAM controller controls the memory layers on top of it. And what we're going to do is we're going to add a very simple in-order core to each of the vaults. And these cores can communicate with each other through the network. And what you can do is, to scale the system, you actually connect many of these hybrid memory cubes together. And then you connect this accelerator to a host processor, just like a GPU, let's say. So you offload your graph processing to this host to this accelerator. And on top of this, you lay out your graphs, and graph nodes stay where they are. So whenever you want to do a computation on a graph node, let's say you want to update a graph node, you send a message to the processor that houses the graph node on top of it in the memory layers. So you never move the data over here. You move the computation to the data. Of course, you move the intermediate data to operate, but you don't move the graph nodes themselves. Graph nodes themselves stay in memory. As a result, we get rid of data movement significantly. We change it to an instruction movement problem. Of course, graph partitioning becomes important. How do you partition your graph is really important over here. And later works actually improved on our work, to, showing that you could actually do much better than what we have suggested. But let me show you what we have done. Basically, we do communications via remote function calls. We send instructions to the data such that we can update the graph nodes without moving data. And we have some prefetching mechanisms that I'm not going to talk about. And these are the systems that we evaluated. These are the baseline systems. As you can see, they all have the processor memory bottleneck. As a result, they're limited by the memory bandwidth. But Tesseract system that we named it as is different. You can see that the processor memory dichotomy doesn't exist over here. Processor and memory are on the same node, and you basically communicate with each other to minimize data movement. And you can see that the bandwidth that the nodes that in the logic layer have, the cores in the logic layer have access to is very significant, 8 terabytes per second as opposed to 640 gigabytes per second. Now, this leads to significant performance improvements on real graph processing algorithms, 5 of them. Basically, we get about 13 to 14x performance improvement. And these are actually stale results in the sense that this is 5 years old. There's been a lot of work in the field showing that, oh, you can improve the system by doing better graph partitioning, better load balancing, better partitioning of the computation, et cetera, et cetera. And today, I believe we're actually more than 2 orders of magnitude if you add up all of the benefits that other people have contributed on top of what we have contributed. So essentially, you can improve graph processing performance by more than 2 orders of magnitude by processing near data. And I'm going to skip this, but there's a lot more analysis in the paper. There's a lot more room actually for improvement. And energy is another story. Essentially, by not moving data and transforming the problem to an instruction movement problem, you actually reduce energy by almost an order of magnitude. And again, newer works improve this much better than we did. You can take a look at those works. And if you're interested, I'd be happy to send you those works. Okay, let me talk about one more thing here. Maybe not aggressive as I described, because the previous one I described actually is very aggressive, right? It's basically changed the programming model completely. Now you're actually programming as a distributed system, similar to how data centers are programmed, but you're doing it on chip or on the node, let's say. And also we get rid of virtual memory, for example, where it's all physically addressed. It's like an earlier form of GPU. I think over time, these things can get adopted, but it's always good to also look at more adaptable solutions. And I mentioned this paper before, where we examined a bunch of workloads, and these workloads are really important, especially on mobile devices. And you can see that browser, video playback and capture, and machine learning inference are the workloads that we examined. And we basically found out that more than 60% of the entire system energy is spent on data movement. And if you want to actually have compute units inside or close to DRAM in the logic layer, we have a big challenge in a mobile system. You have limited area and energy budget. So this work is very cognizant of the area and energy budgets that we have. So the second observation we have comes to the rescue. Basically, it turns out a significant fraction of the data movement often comes from very simple functions. And we want to offload those simple functions inside memory. Maybe we can offload them in a small low power core, or simple accelerators that are fixed function, or a combination of both. And I believe actually reconfigurable logic, in addition to a combination of these, is very important going forward. And the takeaway is, if you actually identify those simple functions and offload them, you get about 2x performance improvements. That's the translation of what is written over here for you. About 2x performance improvement, about 2x energy reduction. It's not 13x or 200x, as I mentioned, but it's not bad because you're not changing the entire system. And let me give you an example of some of these functions. I'm not going to go through detail because we don't have a lot of time. In, for example, inference, machine learning inference, data packing and unpacking and quantization consume a lot of time. And those are the things that we offload. And these actually are very offloadable because they're very simple operations that can be done very efficiently close to memory. Actually, sometimes inside the DRAM also. In this work, we didn't explore inside the DRAM chip itself, but you could do it in the logic layer very easily. Quantization is an operation that takes a lot of time, and the paper has a lot of analysis. And again, this is a very simple operation that could be relatively easily done in the logic layer. And okay, I've given you the results. It's about 2x. But you can also see some of the other examples here: compression, decompression, texture tiling. And you can see that in video playback and capture motion estimation. So some of the functions are relatively specialized, but as long as you can identify your functions and offload them to the logic layer, you gain significant benefits. Okay, so if you're interested, you can read the paper for more. So clearly, this idea is applicable to GPUs also. I'm not going to have time to talk about those. And we've also looked at accelerating pointer chasing, which is really hard to improve performance and reduce the energy of. Doing it in 3D stacked memory is very beneficial. You can do this automatically in some way. And you could actually do this for maybe sometimes even more interesting and large-scale applications like climate modeling. And as I mentioned earlier, approximate string matching is very interesting, and time series analysis. So there are many, many examples, as you can see. Now, let me quickly talk about some adoption issues in processing in memory. And this leads to what is the minimal thing that we can do? I'll give you the idea over here. Basically, if you want to change the system minimally, with minimal cost, minimal changes to the system, no changes to programming model, the idea that we had developed was to actually add instructions that can be executed either in the processor or inside memory. We call this PIM-enabled instructions. These are by nature first executed by the processor. They're cache coherent, they're virtually addressed, but we restrict them to operate on a single cache block to solve a lot of the adoption issues in memory. So this requires no changes to the sequential execution model, no changes to virtual memory, minimal changes to cache coherence, and no need for data mapping. These are all adoption issues related to processing in memory. And then we also have another mechanism that actually enables dynamic execution. You dynamically decide where to execute this best. And I'm going to leave you to read the paper to do that. And let me give you an example from the earlier graph processing workloads. Here, for example, the programmer can say, okay, you add PIM, or you do the PIM, this potentially PIM operation is a PIM-enabled instruction. And this is the existing programming model. It doesn't change anything. We already program with fences. We already program with adds, except now we add a designation that this could be executed in processing in memory. And you could see that there are some other instructions that may be interesting. For example, Euclidean distance computation is very important in time series analysis. Dot product is very important in machine learning, and hash table probing is very important in databases. So depending on your application, you can specialize these instructions. And initial evaluation results are very promising. You get essentially about, let's say 50% average speed up and 25% average energy reduction. So it's not as good as 2x clearly earlier, or 13x or 100x, but it's not changing the system significantly also. Okay. So this is a much more adaptable solution going forward. So since processing in memory is a paradigm shift, it's always important to examine adaptable solutions. And that brings me to the next topic. How do we eliminate the adoption barriers? This is in one slide, the barriers to adoption. I think we need to examine, since this is a topic that spans all the way from algorithms to devices, I think most of these are still related to software aspects. What kind of functionality do we need? What kind of software can we write? How do we ease programming? What is the compiler and hardware support and interfaces that we need? What is the system support that we want to provide? How do we actually enable coherence and virtual memory? Okay, what is the runtime support, compilation systems, and what kind of infrastructures that we need to get the benefits and feasibility? I believe all can be solved with a change of mindset. We just need to start simple and start solving the problems. And I believe clearly we need to revisit the entire stack, but we don't need to revisit the entire stack immediately at the same time. We just take steps in different directions. For example, row clone and ambit are relatively small steps, and PIM-enabled instructions are relatively small steps. Okay, if you're interested, we have this PIM review and open problems that we have written about in multiple papers. So there's good news. There are actually companies that are producing real DRAM chips. We're working with one of them. This is called UPMEM. They're based in Grenoble in France. And they already have DRAM chips that are augmented with what they call data processing units. They actually had a hot chips presentation in 2019, which I linked to over here if you're interested. And these folks actually have produced these DRAM chips today and can actually do large-scale data parallel processing in these processors that are connected to each bank in a DRAM chip. So if you're interested, I'd be, again, happy to talk about it. And we have some works that are going on in this area. So clearly there's interest in the industry and startup space on this also. And this is something that was, in my opinion, unimaginable for decades and decades. But now we have actually startups that have produced these chips and they're working in the lab for sure. Okay. So there are many challenges. I'm going to skip these over here. You can take a look at the slides. They will be available. Clearly, this is not an easy issue, but we want to enable computing architecture with minimal data movement. And for that, we need to do some work. If there's some time, I will continue and very quickly give you an idea of these. If not, I will skip to the conclusion. Tim, what do you think? I can take 5 minutes.
Yes, yeah. 5 minutes is good.
Okay.
So if we can conclude in 5 minutes.
Okay, sounds good. Yeah. So very quickly, I will cover these topics very quickly in 5 minutes. I will not do justice to them, but these are also very important topics and very good research directions. So the first topic is how do we design more intelligent architectures by exploiting data? So system architecture design today is human-driven. Humans design the policies. As a result, all over the system, we have many simple, short-sighted policies. And as a result, we don't have automatic data-driven policy learning in our cache controllers, memory controllers, SSD controllers, etc. As a result, there's almost no learning. The system cannot take lessons from its past actions. The key question is, can we fundamentally design intelligent hardware architectures? I believe an intelligent architecture is data-driven. Machine learns the best policies, how to do things. As a result, you get sophisticated, workload-driven, changing, far-sighted policies that can adapt to the environment and adapt to the systems. You have automatic data-driven policy learning. All controllers are intelligent data-driven agents. So the key question is, of course, how do we start? So let me give you an example of work that we done 12 years ago. This is called self-optimizing memory controllers. Again, I'm not going to do justice to this work, but memory controller is actually a very important part of the system. All of the requests go through memory controllers to access memory. And it's not easy to design because there are many, many things that you need to keep track of. Timing constraints, resources, refresh, power management, performance and quality of service optimizations. So you can read some of the papers that I mentioned over here if you're interested. And the design of this is becoming very difficult because there's heterogeneity in the agents accessing the memory controller. There's heterogeneity in the memories themselves. And there are many goals at the same time that we want to satisfy for different agents. So as a hardware designer, you could start actually screaming. And essentially, the reality is that it's difficult to design a policy that maximizes performance, quality of service, energy efficiency. Too many things to think about. Even if you optimize for one workload, another workload comes and your policy becomes inefficient. Our dream was, wouldn't it be nice to design a memory controller that can automatically find a good scheduling policy and so on? And the idea is relatively simple. This was published in ISCA 2008. Basically, it's a memory controller that adapts its scheduling policy to workload behavior and system conditions using machine learning. And we use reinforcement learning because it maps nicely to memory control. And memory control is essentially a reinforcement learning agent. It dynamically and continuously learns and employs the best scheduling policy to maximize performance. So we're all reinforcement learning agents as humans. Basically, we observe our environments, take an action based on a given state, and get a reward or punishment. Punishment is essentially a negative reward, for example. And based on that, we decide what action we can take in a similar state in the future. Essentially, we're going to do the same thing for memory controllers. And memory controller is a nice Markov decision process that fits very well all the theoretical guarantees provided by reinforcement learning, and we implement the reinforcement learning in memory controller to maximize the long-term rewards. Again, I'm not going to go into detail. You could do this. The paper discusses it. You need to decide the states, actions, and rewards. And the tough part is really the reward function, in my opinion. Other parts really can be automated by machine learning techniques today, but reward function is the tough part for the designer themselves. And in the end, it turns out you get large, robust performance improvements over many human designed policies. And of course, there are advantages and disadvantages that I'm not going to talk about, but if you're interested, take a look at the paper. I believe there needs to be much more other examples of this to design an intelligent architecture. We need to really rethink the design of all controllers that we have. Okay, so this is an example of data-driven computing architectures. Let me talk about the third one very quickly. I call this data aware. essentially, we want data awareness such that architecture understands what it can do with and to each piece of data. As a result, it can make use of different properties of data to improve performance, efficiency, and other metrics. And there are many, many metrics of data, as you can see. So today, unfortunately, higher level data information is not visible to hardware. We may have information about data structures, access patterns, data types, code optimizations, semantics like security, approximability. None of them get communicated through an interface. Today, we're actually stuck with ones and zeros, instructions and memory addresses. So we want to actually widen the interface while keeping it efficient, such that it's much more expressive, such that we can actually provide a lot more information about higher level data to the hardware. And we did this in this paper. This paper is one of the starts, and you can take a look at it. And if you actually communicate this information in a general purpose manner through an expressive interface, you can enable many optimizations, which I really don't have time to go over. And we did this as an example with GPUs together with NVIDIA. This is called the locality descriptor, and NVIDIA is actually implementing this in their future processors. Basically, we can express locality of different data structures, and underlying GPU, both at the system level as well as the architecture level, can do the allocation of memory intelligently such that it can maximize locality. Hybrid memory management is another example of this. You need to actually know the characteristics of your data to achieve the best of multiple technologies, as you can see over here. And you can, again, look at examples from prior work. For example, one example is if you know the vulnerability of the data and the tolerance of the data to memory errors, you can actually communicate that to the system, and the system can allocate the data to different types of memory, like reliable memory versus low-cost memory. And then you can get improvements in terms of performance or cost or energy and efficiency. And if you're interested in that, again, I'm going through this relatively quickly, but you can look at this paper. And finally, I'll give you one more example. This is actually very, very important, in my opinion, for artificial intelligence applications, because neural network evaluation is very memory intensive. And there's actually very wide variation in terms of the characteristics of the data. Some layers are very tolerant to errors, some layers are not tolerant to errors. On layers that are tolerant, you can reduce memory latency and voltage significantly while still achieving a user-specified DNN accuracy target by changing the training of the system, the training of the neural network. And this is an example of data-aware management of memory latency and voltage for deep neural network inference. And you can see examples that we provide in our paper. This is for ResNet. You can see that some parts of the weights and feature maps of ResNet are more tolerant over here. Some parts are less tolerant. And if you actually know the tolerance somehow, and you can figure this out actually, you can map more LA tolerant layers to the memory parts of the lower voltage and latency. And we've done that. And as a result, we get significant performance and energy improvements in this work. Okay, if you're interested, there's more in this area that I don't have time to talk about, but these are examples of data-aware architectures. So let me conclude now. I think I've talked about all of them. Maybe I didn't do justice to the last two. This doesn't mean that they're not important. I would encourage people to actually look into these directions in addition to this first direction, because they all span across the stack in the end, all the way from algorithms to devices, all three of these directions actually. Okay, let me conclude. I'll take a couple more minutes, Tim, if you don't mind. Hopefully this will be interesting.
Sure.
Okay, a famous architect once said architecture should be based upon principle and not upon precedent. Precedent is what comes before, principle is clearly principle. And this architect is Frank Lloyd Wright. He is perhaps the most famous American architect of the 20th century. And if he were designing things based on precedent, he could have designed something like this. It's not bad, it works. I mean, I don't mind having this clearly. It's processor-centric, I would say, and from the analogy perspective. But his masterpiece is this. He didn't design the previous one. He designed this thing. And this is called falling water. It's very close to CMU, where I used to teach, and I used to start my lectures talking about this. And you can see that there's a principle in this architecture. It's organic. It's very, the architecture is in harmony with its environment, as you can see. And you can read about it if you're interested. Now that I'm in Zurich, I talk about train stations. This is a precedent-based architecture. It's not bad. It works. It's processor-centric, let's say. But maybe it's not like this. This is, I believe, I go through this once in a while in Zurich. It's Bahnhof Stadelhofen. It's beautiful. There's another principal design from the same architect. You can see some principles coming up. Another principal design in Valencia. Another principal design in New York City. This is Oculus. And the architect is Santiago Calatrava, who's an ETH alumnus. And there's a principle in these designs. So I will posit the question. I don't know the answer to, do we have the overarching principles for computing today? I don't believe processor-centric design is the overarching principle, yet that's the only principle that we really use in all of our systems to design our systems. And we should probably be searching for other principles. I believe data centricity is a principle. Heterogeneity is another principle. I have actually a list of these things, but of course, I don't claim to know all of the principles, right? But I will conclude by saying that it's time to design principled system architectures to solve the data handling problem, which manifests itself as a memory and storage problem, and it's going to become much worse into the future. It'll affect our sustainability going into the future. We want to design complete systems to be truly balanced, high performance, energy efficient. We want intelligent architectures. And I believe at least 3 principles need to be at play: data-centric, data-driven, and data-aware. And we want to especially enable computation capability inside and close to memory. I believe this can lead to orders of magnitude improvements, and I've shown you several examples of this. This can enable new application and computing platforms, for example, platforms where we can do genome analysis within a minute on our cell phones. This can enable a better understanding of nature as well, in my opinion. I don't believe with processor-centric principles we can understand nature, which I believe by nature is not processor-centric, and who knows what else. So I believe we need at least 3 principles, but we perhaps need to discover other principles. And while doing so, I believe we need to revisit the entire stack, but we can get there step by step. And these are some good principles that I derived over here. Some of these are already employed in processors, for example, better than worst case design. But I believe you need to actually employ many of these principles, and better cross-layer communication all the way from algorithms and devices are going to be really important to enable many of these at the same time. But most importantly, I believe you need open minds. You need to be open to innovation and enable that innovation in a strong way going forward. Okay, I will conclude by thanking people who have been funding us. Please keep funding us, and thanking my students and my group and my collaborators who have contributed to essentially all of the work that I've described. And if you're interested, you can read more about our work in this newsletter. Okay, thank you very much. I'd be happy to take questions.
Onur, for the excellent talk, a lot of information. And I'm pretty sure when you come to Hong Kong, we can ask you to give a couple more talks focusing on the data-driven and the data-aware part, which you already covered, but I can sense that there are a lot more you skip. Also, to all the audience and students, with Onur's approval, actually, we're going to post a video as well as the slides made available. I know you have a lot of references and slides and papers. You flash through that, which are very informative, but I believe people will like to get a reference. So
yeah, absolutely.
Yeah, so we will share the slides and the video. So with that, we already saw a few questions being raised in the Q&A. I don't know whether I know you can see them, but
I can see them, but I didn't get a chance to read them so far.
Yes, maybe I start out. I quick pick maybe 1 or 2. One question in general would be about PIM. Is what are you talk a little bit about the barrier for acceptance, right? But are there current commercial VLSI flow or design flow for PIM? I think how would we be able to use existing design flow, commercial flow with minimum modification to accomplish design? I think that's one question.
Sure. So I think you're talking about how to accomplish the design, not the programming, right?
Yeah.
Yeah, I think that's a great question. As far as I know, there's no design flow at this point. I know some folks are interested in developing it, but as far as I know, there's nothing openly available. But I believe also this is a really good research problem as well for EDA systems. For example, there's some work at EPFL in Nani De Michele's group that looks at logic synthesis using majority functions. And we've been looking at that. They've been looking at it from a logic perspective, but what they've done is actually it could be useful for what I've described in the bulk bitwise operations also. So we've been looking at converting that. But again, I think there's more room for doing this. So as far as I know, there's no design flow. People do it in a custom manner. For example, the UPMM folks, in my opinion, they have done it in a custom manner without going through a design flow.
Great, thank you. This was a question from Zhiyang Hong. Then I'll move on to a question from Tingyuan Liang. There were 2 questions. First is that it seems many attacks targeting at the row hammer, assuming that the memory rows are in regular layout. People been thinking about overcoming the row hammer problems by changing the layout, make it a little bit irregular instead of just the controller part.
Mm-hmm. Yeah, there have been some works such that you could separate things from each other. But I think maybe if I understand the question right, you could, for example, randomize the layout. But there are people who, the folks who are working on security are very smart. They always find a way of actually finding, reverse engineering how the layout actually happens. And as a result, they're able to launch the attacks.
So I think the question specifically, I don't think it's referring to random instead of it talking about irregular patterns of memory layout. That's what I read. So the hackers might fail to figure out where they are attacking. But as you pointed out, the reverse engineering always a possibility to figure out, right?
Exactly. Yeah, I think I mean randomizing actually is a way of that has been proposed in the past, but people actually find ways of actually getting overcoming the randomization to reverse engineer. So I think just solving it at the memory layout. I mean, personally, I don't think it's going to be secure enough, but that could be part of a bigger solution, of course.
So another second question from the same person is for the in-memory computation, element-wise or bit-wise operations are hot in research area. What about the data movement inside memory? For example, whether the data movement inside will be a bottleneck in the future for some workload and applications?
Yeah, I believe so. And I think I didn't go through a lot of other works after row clone, but that's an important research area also, because we will be bottlenecked by data movement, especially if we want to do more computation inside memory. I believe we need more interconnectivity between memory banks, memory subarrays, and even memory modules going forward. And I think that's a very good area to investigate. I didn't mention this, but we have some work interconnecting subarrays, for example. It's called LISA, low-cost interconnected subarrays. It was an HPCA 2016. And there, with 3D stacking, you can actually do even more. You can actually have a network connecting banks. We have work this year that looks at this, but there are also other works in the field. So I think that's a very good topic to look into.
Right. The next question, there are a lot of good questions here, but I just randomly picked. Sure. Ziwei Liu from UC San Diego. He said that you mentioned that memory system for intelligent application like machine learning. I'm wondering how memory that would be suitable for such intelligent tasks differ from memory for traditional tasks. And I think based on my interpretation, let's say just for deep learning, you mentioned a lot about DRAM work in the memory-centric PIM, etc. But if let's focus on deep learning from the workflow, from the network architecture is very, very different. Just coming from CPU to GPU to all this deep learning flow. So how would that memory play the differences? How general what you talk about can be applied to deep learning, for example?
Yeah, so that's also a great question. Basically, I think, I mean, certainly there are two directions here. One is designing memories that are general enough to do some operations and mapping applications to it. I think then any kind of application can be mapped, including deep learning. But of course, I don't think that will be the most efficient design, memory design, or memory plus computation design for deep learning. If you really want to design some system for deep learning, I believe you really need to customize the memory for that purpose also. And in that, I think once you go over there, maybe you should really be doing more than what we've discussed, bulk bitwise operations. Maybe you should really be adding multiply and accumulate units and data movement mechanisms across different components. So maybe a memory plus compute unit put together that can be connected in a systolic array fashion that could actually, where your neural networks can be mapped much better into, could be a design option over there. Of course, this will increase the cost of your memory, but again, you may get significant energy efficiency and performance improvements. So that's my take on it at this point. And I think some similarly customized memories are being investigated, especially in the emerging memory technologies area. I don't know of a lot of works that look at DRAM. How do we actually completely redesign DRAM, for example, just for neural networks? I think that's a very good direction also. So basically, I don't have the full answer, but I kind of sketched a potential direction.
Right. I'm looking at the watch. We have 4 more minutes before 6:30. That's where we intended to end. So maybe I ask one question. You referred earlier that there are certain non-volatile emerging memories which are very suitable for future computing, such as the PCM, STT-MRAM, RRAM, etc. So, but these devices, I think, very, very active research area, has a fundamental problem of reliability in certain aspects, and for magnetic RAM has been there for a while. Therefore, how you see the pathway of these devices gradually getting into mainstream in the moving into the future, or if they, based on your prediction, will ever make it into mainstream, like flash and the DRAM? Yeah,
that's a very good question. It's the $1 million question, maybe, right? So I think I'm optimistic. I think these memories have advantages and also disadvantages. At some point, I think their benefits will be good enough as a hybrid as part of a hybrid solution. I don't think they're going to be immediately able to replace DRAM, for example, or flash, frankly. I think they will need to be somewhere hybrid. And I believe they will need to be general purpose enough so that they can actually be produced at a mass volume. So I think, for example, them being good enough just for deep learning may not be enough to actually enable them in the larger scale, from my perspective. Of course, that's a really important application. But I think they will need to be somehow general enough so that we can take advantage of them in most of our computing devices. I don't know if that answers your question, Tim, but
yes, no, definitely. I think it's more than $1 million question. I think it's a $1 trillion question for the entire industry.
Sure,
so
yeah.
I will ask the last question on behalf of the students who are in the early stage of their research, which I think John Hennessy and David Patterson, that in their Turing Award lecture last year, project another golden age for the field of computer architecture in the next decade. So that excited a lot of students making a decision to invest their career in this direction. So I'd like to hear from you as a computer architect that is that what you believe too? I guess so. But then if that's the case, in your opinion, what sub areas and topics within the computer architecture would be the most exciting direction that you can share your thoughts with the students who can learn from you? That's probably will be a suitable last question to close today's session.
Sure. So I think that's a very good question. I mean, I cover this in my computer architecture lectures a lot. I noticed some students actually mention them in the chat, just looking at it. So I think I absolutely agree. I think computer architecture is today an outstanding field where you can have significant impact on the field and do a very exciting research. Because if you look at the picture that I'm showing over here, computer architecture sits in the middle of it. And in my classes, I said computer architecture should not be considered just the software-hardware interface and microarchitecture, but we should really take the expanded view of architecture. It's really spanning all the ways from algorithms to devices, enabling innovation at the bottom as well as innovation at the top. So I think essentially computer architecture is an outstanding place to be today. This was not the case when I was doing my PhD in 1990s, for example. At that time, well, I was studying, not PhD in 1990s, but I was studying computer architecture in 1990s. At that time, the paradigm was clear, right? Which clearly changed. It was a single core superscale out of order processor, and everybody wanted to improve that. But over time, it changed. It became multi-core. Today, we don't have a paradigm that is dominant. And as a result, you can innovate a lot in the field. especially if you take this expanded view that I mentioned, going from all the way from algorithms to devices and enable the communication between algorithms to devices in a much better way. I think this is going to continue for a really long time, as long as we have problems at the top, which we will, and technology scaling problems at the bottom, or new technologies coming up that need to be enabled, which we will also. So both of them are not going to change. And I think architecture is going to be a very good field going into the future. So what to investigate given this? I mean, clearly everything that I described in this talk is something that I passionately believe is important, and it can change the field, it can change the paradigms. So everything we discussed is important, I think. On top of this, I think anytime you can think of enabling something across the stack, algorithm through devices, I think that's also important to investigate. So we can do fundamental research in how to enable the systems that are going to be the systems that we're going to use in the future. So something that I did not fully touch in this talk is security, for example. Security is another problem that spans across the stack. I mentioned this with the Rowhammer, but again, that's another thing that should be investigated, going all the way from algorithms to devices. And reliability is another one that I briefly touched. So I think the problems abound. Great. I hope that covers the space.
Great answer. Due to the time limit, I think we need to close today's section. Yes. 90 minutes is too short. So on behalf of all the audience, I'd like to thank you, Onur, for the very, very exciting talk, and also appreciate that you're willing to share the material with the audience. And next time when you come to Hong Kong, we will for sure to get you to talk about the data-centric, data-aware and data-driven part, which I think I'm very much looking forward to it. Thank you again. And because it's webinar format, I don't think you will hear the pauses from the audience. But I'm sure, I look at most of them still stay all the way to the end. That shows how exciting the talk has been. Thank you.
Thank you very much, Tim. Thank you very much for inviting me, and I look forward to meeting you in person in Hong Kong as well. And thank you everyone for listening.
Yes. So just a final word. This is Billy from Hong Kong Science Park. So when you all leave the webinar, we will have the system will prompt a survey for you to fill up about your comments about this webinar today. So just spend a few minutes of your time to fill up the survey that will help us improve. So Professor Yang and Professor Mutlu, I think that's the end for today. Thank you very much for your time. Thank you all.
Thank you very much, Billy.
Okay, thank you.
Bye-bye. Okay, bye everyone.
Okay, bye-bye.